Question 15. So in part 1 we're going to work out the coordinates of Q. And to do that we have to work out where B is first. So the angle that B is at is theta plus pi on 2. So we can say that B is at A cos theta plus pi on 2, A sine theta plus pi on 2, because it's on that circle where the coordinates are like that. Now, to work out what this is, I mean, personally what I would do is just look at like the y coordinate here, so that distance there is the same as that distance, because this is just that triangle rotated. And then this distance is the same as that distance. So I can see that the x coordinate of B is just the y coordinate of A, but negative. So it's going to be negative A sine theta. And the y coordinate, so that distance, is just the same as the x coordinate here, which is A cos theta. If you wanted to like show working for that bit, I don't think they did show working in their solutions, but if you wanted to show working, you could use the angle sum formula, or you could say that this is, that's like cos of pi on 2 minus negative theta, and then that's sine of negative theta, which is negative sine theta. You could do that sort of thing, but I don't think you really have to show working there, so you might as well just do it geometrically, which I think is a lot faster. Okay, so we get to the coordinates of B, and then the x-coordinate of B and Q is the same, because Q is just directly below B. So we can say at Q, we've got x is negative A sine theta, and then we can plug that into this formula for the ellipse. So we've got A squared sine squared theta on A squared plus y squared on B squared equals 1. So those cancel, and then we can move that over the other side since we're solving for y, and we get y squared on B squared is 1 minus sine squared, which is cos squared theta. And then we can shift over the B squared. So y squared is B squared cos squared theta, and so y is square root of that, which is B cos theta. If y is greater than 0, it would be negative B cos theta if y is negative. But we can see that like Q is meant to be just directly below B, so the positive solution rather than the negative solution, that would be right down there. Okay, so that gives us, yeah, so then you could just have a conclusion line saying therefore Q is that. So that's part 1 done. For part 2, what I would do there is think of angle P or Q prime as being composed of that one and that one. So I might just draw a little diagram here. It's a very badly drawn ellipse. So that we can say like, so like there's P and there's Q prime. And I'm going to say that's alpha and that's beta. So just give them some names. So we could say tan angle P or Q prime. I mean, the arctan there is a clue that we need to think about the tan of that angle. So that's tan of alpha plus beta. And then you can use the formula for that. So that's tan alpha plus tan beta over 1 minus tan alpha tan beta. Okay, and then tan alpha is going to be the y coordinate of P divided by the x coordinate. So P was A cos theta, B sine theta. So that's going to be B sine theta on A cos theta. That's the tan alpha. And then for tan beta, that's going to be, as the coordinates of Q prime. So it's going to be like the absolute value of that divided by that. Because we're just interested in that as a positive angle. I mean, you could also do it like define that as being the negative angle, and then it's going to be alpha minus beta there. But I'll just do it this way. So if you think of that as being the positive angle, then you just want like that distance rather than that as a coordinate, if you know what I mean. Okay, and then that's on 1 minus tan alpha, which is that, times that one. And then that cancels with that, that cancels with that. And at the top we've got like a b on a. We can take that out the front. So sine theta and cos theta. It's cos theta and sine theta on 1 minus. So we've got b squared on a squared. Now, what we could do there is put them on a common denominator. And actually what I might do is multiply top and bottom of this by a squared, because that's just going to clean everything up and get rid of these fractions. So you'll get ab, and then let's do like over cos theta sine theta. So you'll get sine squared theta plus cos squared theta, which is 1. Alright, now we want to minimize this, so we have to think about what's going to happen for different values of theta. And the easiest way to work out what's going to happen to this is to write this in terms of sine 2 theta. So sine 2 theta is 2 sine theta cos theta. So if you think of that as being, I might just like put this out here. So we'll have ab on a squared plus b squared times 1 on, this is half of sine 2 theta. So, and then actually we could, let's get rid of that half, multiply top and bottom of that by 2, so we get 2 on sine 2 theta. Now, so that's tan angle POQ prime. So you could say that angle POQ prime is minimized when sine 2 theta is maximized, which is when it's 1. So we've got tan angle POQ prime is just the 2ab on a squared plus b squared when sine 2 theta is 1, because that's just 1. And then you could say, okay, therefore the minimum POQ prime, angle POQ prime, is the arctan of that. And that's it for that one. Part B. So de Moivre's theorem, if we want to work out sine 8 theta, then you just want to say cos 8 theta plus I sine 8 theta is cos theta plus I sine theta to the power 8. And then let's use the binomial theorem there. So the sum from k equals 0 to 8 of h is k cos theta. Let's do that to the power 8 minus k. Then we've got the I sine theta to the power k. Now we're just interested in the imaginary terms there. So if you like, when k equals 0, you're going to get I to the 0, which is 1. So that bit's real. We don't care about that one. When k equals 1, you're going to get I to the 1, which is imaginary. When k equals 2, you're going to get I squared, which is negative 1, which is real. So you can see we're only interested in the odd terms, because that's when we're actually going to get an I in there somewhere. So you can actually just say I sine 8 theta is the sum from k equals 0 to 8, where k is odd. So just restricted to the odd terms. And then let's expand this bit. So you got I to the k sine to the k theta. And then, so yeah, let's work that out. So we just need to plug in all the odd values of k between 0 and 8. So 1 would be the first one. So you got cos theta to the power 7 and then I to the 1, and then sine to the 1 theta, so just sine theta. And then we've got where k equals 3, cos the 5 theta. I cubed is negative I times sine cubed theta. And then we've got h is 5 cos cubed. I to the 5th, I to the 4th is just 1, so I to the 5th is just I. We've got sine to the 5th theta, and h is 7 cos to the 1, so just cos theta. I to the 7 is negative I times sine to the 7 theta. Okay, and then let's just get rid of all the i's from both sides. So, like, just get rid of those i's. And then that gives you that. So you would just, write that out again. Okay, for part 2, we can say that sine 8 theta and sine 2 theta is all of this. So let's work out what these coefficients are. So h choose 1 is 8. And then we've got h choose 3, which is 56. You can just do those on your calculator if you want to. Then we've got 56 again. And 8 again. And all of that is over sine 2 theta, which is 2 sine theta cos theta. Okay, let's simplify that. So, that divided by that is 4 cos to the 6 theta. This is the kind of question where in uni we would refer to this as cranking the algebraic handle, because it's just such a mechanical task. Like, it's just, you just grind and eventually you get to the end. I really don't like this question, if I'm honest. It doesn't require much creativity, and it's just algebra. Okay, so that one divided by that, we got 28 cos squared theta sine to the 4th theta. We got that one divided by that, it's minus 4 sine to the 6th theta. Alright, we've got a factor of 4 that we can pull out the front. It's going to make things a bit simpler. Now we have to write everything in terms of sine. So this cos to the 6th, you can think of that as cos squared theta to the power 3, and cos squared is 1 minus sine squared. So we've got 1 minus sine squared theta cubed. That divided by 4 is 7 cos the 4th theta. Similarly, we think of that as 1 minus sine squared theta squared. And then that's 1 minus sine squared. And minus sine to the 6. Alright, and then we just need to expand all of this. So, 1 minus 3 sine squared theta plus 3 sine to the 4th theta minus sine to the 6th theta. And then we've got this bit, so minus 7 sine squared theta from that times that. And then, so this is 1 minus 2 sine squared theta plus sine to the 4th theta. You can do this expansion in 2 steps if you like. I'm just sort of trying to rush through it. So you've got the minus 7 times the minus 2. So that makes plus 14 sine squared times sine squared sine to the 4th. And then we've got the minus 7 sine to the 4th times sine squared, so minus 7 sine to the 6th theta. And then we've got this bit, so plus 7 sine to the 4th minus 7 sine to the 6th, and minus sine 6 theta. So we've got 4 times. That's the only constant term in there, so just 1. For the sine squareds, we've got that one and that one. I think that's all, so minus 10 sine squared theta. Sine to the 4th, we've got a 3 and a 14 and a 7, so that makes 24. And then sine to the 6th, we've got -1, -7, -7, and another -1, so that's -16. And hopefully that was what we were trying to prove. Yes, okay, so that's it for that one. Part C. So I actually did this one a different way from what the solutions say. I just did it by expanding the right-hand side, so you can say the right-hand side is, so you've got x plus the x squared plus x cubed plus ... plus x to the n minus nx, and then you've got -1 minus x squared, and so on, up to x to the n minus 1 plus n. So you can cancel that with that, and that with that, and so on, up to the n minus 1 there. So you'll get x to the n minus nx minus 1 plus n. And then that's just, we just have to put that in that form. So x to the n minus 1 minus n, x minus 1, which is the left-hand side. Alright, for part 2, if you think of this, like if you move that over the other side, then it's just that greater than or equal to 0. So we want to show that this bit can't be negative. So often, like, I sort of try a few values to get like inspiration for how to prove this. So you would see that when x is bigger than 1, this bit's positive, and all of this, you've got like a bunch of numbers that are bigger than 1, and there's n of them, so they add up to something more than n. So that minus n is also going to be positive. When x is less than 1, I mean, it still has to be positive, so it's between 0 and 1. This bit's going to be negative, and this bit here is going to add up to something less than n, because all of these bits are less than 1. So here you're going to get a negative number as well, so you've got negative times negative. So we have to actually split it up into 2 cases, one where it's where x is greater than or equal to 1, and the other case where x is less than 1. So we could say something like, okay, for part 2, for x greater than or equal to 1, we've got, you know, we've also got like x squared is greater than or equal to 1, and x cubed is greater than or equal to 1, and so on. So 1 plus x squared plus, sorry, 1 plus x plus x squared, and so on up to x to the n minus 1. That's going to be greater than or equal to 1 plus 1 plus ... where there's n of those. So that's going to be greater than or equal to n. And you know what, I don't want to have to keep writing that out, so I'm just going to say, I should have said this up the top, let s equal that, because I really don't want to have to write that out 50 times. Okay, so then we could say, so we've got s is greater than or equal to n, and then we can say s minus n, get rid of that, s minus n is greater than or equal to 0, and x minus 1, if x is greater than or equal to 1, then that's greater than or equal to 0. Therefore, x minus 1 times s minus n is greater than or equal to 0. And what are we trying to show? Yeah, therefore that's... Actually, let's do that right at the end after we do the other case. So then we've also got for x less than 1, then well, I have to say 0 less than x less than 1. We're going to have x squared is less than or equal to 1, x cubed is less than or equal to 1, and so on. So s, which is 1 plus x squared plus so on, is less than or equal to 1 plus 1 plus dot dot dot, where there's n of those. So we can say that s is less than or equal to n, s minus n is less than or equal to 0, and x minus 1 is less than or equal to 0 if x is less than 1. So then we can say, therefore, x minus 1, s minus n is less than or equal to, sorry, greater than or equal to 0 when we multiply those two. Okay, because they're both negative. Two negatives make a positive. Then we can say, like, therefore, for all x greater than 0, because we've covered all those cases, for all x greater than 0, x minus 1, s minus n is greater than or equal to 0. So that was this, x to the n minus 1. So that's greater than or equal to 0. And then it was asking us to prove x to the n greater than or equal to, just move that stuff over. 1 plus n, x minus 1. And yeah, and that's it for part 2. Now part 3, I actually found that one a bit tricky. I don't know about you. It did take me a few minutes. Let me just clear some space here. And the hard part is working out how it relates to part 2. So what I did is I noticed that this power was negative. So, I mean, for if n is like 2 or greater. So I thought of it as being a to the n over b to the n minus 1. That's the same as that. We're trying to prove, let me just write this out. I mean, you can put this in your rough working. And let's actually expand this, because like there's nothing about n minus or 1 minus n in here. So I'm thinking like that doesn't come directly, that comes from, you know, factorizing stuff at the end. So let's expand that, b minus nb. Yeah, now the way that I actually figured it out was a bit weird. I kind of like, I was sort of trying to apply the same trick that I did here with like factorization. So I thought that like if I shifted stuff around and then it might factorize somehow. I was trying to work it out that way. So I got to the answer in a really circuitous way. But what I should have done was just divide both sides by b here, so that we have a to the n over b to the n. Because then it's totally obvious a over b is the x. So that's what we need to do in the proof. Like this is it's meant to be in that form, 1 plus n, x minus 1, if x is a on b. So we just want to say, let x equal a on b, and then plug that into there. So we've got a on b to the n greater than or equal to 1 plus n a on b minus 1. And then we could just say that's a to the n on b to the n, 1 plus n a on b minus n. And then let's multiply both sides by b. So sort of working backwards in that bit that I did before. if we multiply both sides by b, then we're going to get a to the n, b to the 1 minus n there, because you've got b to the 1 times b to the negative n. And that's b plus na minus nb, which is na plus 1 minus n times b. So that's it for that one. It really did take me quite a while. It took me like 10 minutes to do that. I don't know why. I just got lost. Alright, if you are still confused about any of these questions, then let me know in the comments. And stay tuned for question 16.